previous few lectures, we had been looking at the motion of a single particle, and we saw that given a particle, I essentially get its equation of motion and then solve it to get its velocity or its distance as a function of time. This is essentially what we do, although we looked at constrained motion, motion with friction and things like that. Now we are going to make the problem slightly more difficult. We are going to ask a question: what happens when I have more than one particle? For example, let us take two particles, say of mass m1, connected by a spring, and mass m2 here. You know from experience, if I apply a force on it, it can do 2 or 3 different things. For example, it could either stretch so that particles go farther apart, it can change its orientation, or can do both. And mind you, in all this process, there is a force that is acting on both the particles through the spring, and I am also applying a force on this and a force on this. So how do we go about describing such a motion, and what happens when the number of particles increases? This is what we are going to look at, and a quantity that becomes very useful in describing motions when many particles are involved is momentum. Let me motivate that by taking an example. Suppose I have a cart which is moving on a horizontal track without friction. It is moving with velocity v, and I start pouring some sand or some mass into it. Either I could put it vertically down or slowly put it in. You know from experience that the cart is going to slow down. In fact, if you want to keep it moving with the same speed, you would have to apply a force, and that force is going to be proportional to the rate of change of the mass of this cart times v. On top of it, if the velocity changes, I have to apply more force. Compare this formula with the formula that we have been using so far, which is a constant mass particle moving with an acceleration delta v delta t. So in general, I have to apply a force if I want to move something with a constant velocity but its mass is changing, or its mass is constant and its velocity is changing. To combine the two things, the net force I have to apply when its mass is changing and its velocity is changing is going to be this. I have neglected second order terms in mass and velocity as they go to 0 when I take the limit delta t going to 0. So in general, I can write that the force is equal to d over dt mv. This is the quantity which I define as the momentum of a mass moving with velocity v. So in general, I am going to write F equals dp dt, where p stands for momentum. Let us see how this concept helps me in solving problems in a slightly more convenient way. Let us go back to our example of two masses which are attached with the spring. Let us assume right now that we are not applying any force on the two particles. The only force that is acting between them is through the spring. Let the force on mass 1 be F12 in this direction, and let the force on mass 2 be F21. I am using these indices to indicate F12 indicates force on 1 by 2 and F21 indicates force on 2 by 1. If I write the equations, the Newton's second law equation for each mass, I am going to have m1 dv1 over dt is equal to F12, and I am going to have m2 dv2 over dt is equal to F21. But by Newton's third law, F21 is going to be opposite and equal to F12. So the magnitudes are the same, the direction is opposite. If I add the two equations, I get d over dt of m1 v1 plus m2 v2 is equal to 0. So we get d over dt of m1 v1 plus m2 v2 is equal to 0, and what that implies is m1 v1 plus m2 v2 is a constant. So what we learn is that no matter what the interaction between the two particles is, I have taken it to be most general, F12, F21, as long as Newton's third law is satisfied, is obeyed, m1 v1 plus m2 v2, or the momentum of the first particle plus the momentum of the second particle, which I will call the total momentum of the system, is going to remain a constant. This gives me an insight into the problem. The particles may be doing anything on their own. For example, as we said earlier, they could be stretching, they could be rotating. No matter what they do, this quantity is going to remain a constant. This is the statement of conservation of linear momentum in its simplest form, and when combined with other conservation laws like energy conservation, it gives me a great handle to solve mechanics problems. Let us see what happens if the forces were also applied on each of the particles. For example, I could have on particle 1 there is a force, and to distinguish it from the internal forces between the particles, I will call it F external on 1. Let me call a force on this which is F external 2, and see what happens, what the dynamics of the system is. So now I am going to have d v1 over dt times m1 is equal to F external 1 plus F12, and m2 d v2 over dt is equal to F external on particle 2 plus F21, which, if you recall from the previous slide, is minus F12, and if I add the two equations, I again get that d over dt of m1 v1 plus m2 v2 is equal to F external 1 plus F external 2, which is the total force applied on the system. So as long as Newton's third law is applicable, what I learn is that given a system of particles, so what we see is that the rate of change of total momentum is equal to the net or total force applied from outside, no matter what is happening between the particles. I took an example of a two-particle system. Is it true in general? Let us see. So, suppose I have a collection of particles, many of them, and I apply force on each one of them, external force, which I will call F external on ith particle. In addition, they are also interacting with each other, which I will call the forces on ith particle due to J, so that the net force on ith particle is going to be sum over J, that is force applied by all other particles, but not I. It cannot apply a force on itself. So that if I write the equation for ith particle, it is going to be mi d vi dt is going to be equal to F external on the ith particle plus the forces due to all the other particles, which are going to be equal to summation j, j not equal to I, F I j. To see how the net mass or all the particles move together, I sum over I, so that I write this equation as summation over I mi dvi over dt is equal to F external I summation over I plus summation I j over both I not equal to j F I j summed over. This is a generalization of the formula previously written for two particle system. This you recognize is the rate of change of total momentum P, which I defined as summation of individual momenta. This should be equal to, this is the net external force. So, F external total plus this term I j, I not equal to j, F I j. Let us see what this term adds up to. You can already anticipate it should add up to 0. How does that happen? F I j summed over I and j, I not equal to j, I can write as 1/2 summation I j, I not equal to j, F I j, and just interchange the indices j I, because I am summing over I and j completely, it does not really matter. But by Newton's third law, F I j is equal to minus F j I. So, this term adds up to 0, and therefore, this term is 0, and what we learn then is dP dt for a many particle system is also equal to F external only, where F external is the total force. It is the sum of individual forces applied on each particle. This is a general statement, and you can right away see that if F external is 0, then dP dt is going to be 0, and therefore, net momentum is going to be conserved. So, let us see this again. dP dt is equal to F external total, and if the total applied force from outside is 0, dP dt is 0, or equivalently P is a constant. So, for a many particle system also, if there is no force applied from outside, the total linear momentum is conserved, and that is a fundamental statement of physics. It is used in conjunction with other conservation laws and makes solution of problems easier at times.